let me go start that here. This is extremely important. It's very, very famous theorem of probability theory. So let us see what it is. I'm not going to prove it, right? I'm just going to state the result and interpret it because there's no we've not done all the tools that we need to prove this result. So we will just simply mostly state. So we go back to, we consider again, of course, our the same IIT random variables xi and the same xn. So same xi and the same sn. So sn equal to sigma. So Sn and Xi have the same meaning here also. It's the same Xi that we have, and we are again forming the sum Sn as sigma I equal to 1 to n Xi. But instead of now dividing by n, now we're going to do something somewhat different. So Sn by n, it turns out, has a very small variance. Now to get something with a healthier variance, so let me write here. So we know that we already saw expected value of Sn itself is n into mu, and a variance of Sn, this we already saw earlier. I'm just rewriting this is n sigma squared. So the same Xi as earlier, where let me write here E of Xi is mu, and the variance of the variance of Xi is sigma squared. So the expected value of Sn is n mu, and the variance of Sn is n sigma squared, both of them growing linearly with n. So now we are now going to consider, let me be very clear now. Now we consider a very somewhat different thing. We don't do divide by n. Now we consider this quantity Zn equal to Sn minus, you take the subtract the mean of Sn and divide by the square root of the variance. This is an extremely important parameter, Zn, which is basically Sn minus the expected value of Sn divided by the square root of the variance. So essentially this is going to be equal to Sn minus n mu divided by square root of n sigma squared. Okay, so this is going to be the quantity Zn. Okay. Earlier we were dividing Sn by n and got something which had the variance of which fell with n. But now it turns out that this quantity Zn, right, its variance is not going to fall with n. Okay, so this, it turns out, it means that, right, it's going to have a very important the mean and the variance of Zn are very important now. So it turns out that Zn is going to be is going to have zero mean for all n. Okay, that's obvious because the numerator has zero mean, right? The numerator mean of the numerator. Well, actually, let me rewrite it here. Prove it here. Okay. Okay, so the mean the mean of the numerator is 0, therefore the expected value of Zn is also 0, and equally importantly, the variance of Zn is basically now the variance of, it's the 1 by n sigma squared of the variance of Sn. So note that the variance properties are very important here. We know the variance of Sn when we had it as a separate thing, but if you divide by x minus, if you take a random variable and subtract its mean and divide by the square root of its variance, you get unity variance, right? And therefore this is going to be 1. So no matter how large or how small you make the small parameter small n, right? How many random variables xi you take, right? If you do this, define Zn as we have done on this page, it turns out that Zn will have both zero mean and unit variance. Okay, and this is a very important development, because now it tells us that, right, we are not dealing with a zero, we are not dealing with something which has a variance whose variance is varying with n, right? The variance is now constant, right? No matter how big n is, right, it doesn't change, it stays at 1. And what is the statement of the CLT? This is, we're going to now say it without any proof. Turns out that the CLT state, let me write it here, the CLT statement without proof. What is this CLT statement? That the CDF of the random variable, the distribution of Zn, it tends to, let me put it here, it tends to the CDF of a Gaussian random variable with zero mean unit variance as this n goes to infinity. This is the all important statement, one of the most important statements in probability theory, and one which has profound practical implications, right? That the CDF of Zn has this very important behavior, right? That it, as you make n bigger and bigger, right, you get it, you get convergence of the CDF, right? Convergence of distribution to the Gaussian distribution. So this is, what is this n01? This is basically a Gaussian, right, distribution, or standard Gaussian distribution, right? Zero mean and unit variance. So this is the, right, one of the most important results of the probability, and I think, right, we are going to, let us say, call this central limit theorem as CLT. And what does this mean in practice? Let us just look at that, right. So this is true for any, there's a very general result, right, applicable to any sets of xi, any IID collection xi with finite mean variance. With the mean, okay, we just say with sigma squared, if you, right, with mu, okay, with mu sigma squared finite. So that's the only condition we want, only condition we put on the xi. So it's applicable to, let me just take a simple example. Xi is, let's say, uniform 0, 1. Let's take a look at this, right? So obviously, right, the central limit theorem is going to be applicable to this collection of random variables. the collection of uniform random variables, IID collection U01 random variables, right? And let us see what happens, right? So in this case, it turns out that the mu is half and sigma squared is 1 by 12. So that's the mean and the variance of xi. So what about Sn? Let us look at what's happening. How do we form the Zn now? So now Sn, which is the sum of n of the uniform random variables, always Sn is the sum of n of these xi's. So what is the set of values Sn can take? So Sn has, let's write out the mean and the variance. So E of Sn is n and variance of Sn is n by 12. Both of them, right, linearly increasing with n. And Zn is of course Sn minus n divided by square root of n by 12. Sorry, n by 2. We should put this here. So the mean of Sn is obviously Sn by 2, right? Because each of the mu's is mu is half, so n mu is n by 2. Okay, so this is the random variable Zn that we form. So it turns out that, let me write here, what is the spread of Sn and Zn? So Sn takes values in, what values does Sn take? It's 0 to n. If you add n random IID random variables to the 0, 1 random variables, the smallest value the sum can take is 0 and the largest value it can take is n, right? And Zn takes values, it turns out, is symmetric. That Zn is symmetric now. Let me write it here. I just write the result. What does it take values in? It takes values in minus n by 2 divided by the square root of n by 12 to plus n by 2 divided by the square root of n by 12. Okay. So that is quite clear if you look at the definition of Zn, right? The smallest value of Zn can take is when Sn itself is 0, and at that point if Sn takes a value 0, then the Zn will take the value minus n by 12 divided by square root of n by 12, right? And of course, remember, is in our control. And the largest value Zn takes is when Sn takes a value n, so that is going to be plus n by 2. So this is a symmetric range. So this is going to be the omega Zn. The set of values that Zn takes, right? And it's symmetric, which is the important thing that we want Zn to do. So Zn has a symmetric range, right, for all n, all the way from 1 to infinity, and as of course for small n it won't. It's not going to be, the behavior is not going to be that noticeable. But even when n is as small as let's say even 10. So even for n equal to small, let's say n equal to 10, right? Zn, Zn has a Gaussian, right? Very strong, has almost a Gaussian PDF. Right, the range of Zn, as you can see from here, right, it actually grows the square root of n, right, and I haven't, I deliberately didn't simplify this. You can simplify it, and you will see that this n by root n will become root n in the numerator, and right, you don't have to go for very large values of n. right? It turns out in this particular example that the CLT kicks in even for very small values of relatively small values of n, which is like 10, right? And this can be easily done by simulation or by numerical calculation. Note that the PDF of the exact PDF is messy to find. The exact PDF of Sn, I will just write here. The exact distribution of Sn and Zn is messy, very messy to specify, because you are adding n IID U01 random variables. So it turns out that there is no single formula for the exact PDF of Sn and then Zn, right? And therefore it turns out it's very messy to specify this. It can be done and solved for small n, but it becomes very painful to do for large n. But the point is not, the whole idea of the exercise is not to do the exact PDF, is to look at the approximate PDF as n becomes large. And it turns out that in this particular example, right, Zn has a PDF which is very close to Gaussian, even for small n equal to 10. Okay, and this is a continuous example, right? Now let us consider this is e.g. I've done for the uniform case. Now I do xi being, let's say, Bernoulli. I take the indicator case where xi has Bernoulli PMF with parameter p, right? So that we know that in this case that Sn is binomial. This is very important result. We've done this in this course, that every binomial random variable can be thought of as a sum of n. Every binomial NP random variable can be thought of as a sum of IID Bernoulli random variables with the same parameter p. And so we have this Sn, right? Sn being binomial, and Sn being, and then what does the theorem CLT say about this? So what is Zn in this case? Turns out that Zn is Sn minus Np divided by root of n into p into 1 minus p. Right? We know that the sigma squared. Let me write it here. Mu equal to p. Sigma squared is p minus p into 1 minus p. So these are the values of mu and sigma squared. And if you substitute that in the expression for Zn, you get Sn minus Np by root n minus p. And then this is, right. So turns out that Zn is a funny discrete random variable which takes values in some discrete set. But it doesn't matter. The CDF now, it converges to the CDF of N01 as n becomes large. Okay, so this fact, right, can be used. Means that Gaussian probabilities can be used to, and that is Gaussian. When I say Gaussian, I mean N01 probabilities can be used to approximate binomial interval, right? Interval probabilities of Zn, i.e. probabilities of the type A less than Zn less than B less than equal to B. This can be approximated, right, using N01 probabilities, which are available in MATLAB or whatever, any computing tool will give you Gaussian probabilities, right? And so the so those functions that give you Gaussian probabilities can be used to approximate the interval. So this kind of interval probability of Zn, that is the probability that it takes values between A and B, right, can be calculated using a Gaussian probability. That is one of the important applications of the CLT, right? And of course, an interval probability of Zn can be mapped to a corresponding interval interval of Sn also. Well, that's very easy, which is now this is going to be equal. Let me just write that out. This P is now going to be probability less than Sn minus Np divided by square root of n into np1 minus p less than p, right? So this I can tell, and then this Sn is basically binomial. So basically, right, binomial interval probabilities can be approximated by Gaussian. That is the most important point here. We can also use the CLT to approximate Poisson probabilities, right? So this is the case, the third example. For the Poisson distribution, Gaussian probabilities for Poisson PMF, because it turns out that, right, let me call it here, right, let me say that S is going to be now Poisson lambda for large lambda. Let S, okay, I've already put a let here, let S. So if for large lambda, it turns out that, okay, let me write here, Z is now going to be Sn minus mu divided by square root of, Sn minus lambda divided by square root of lambda. So this is, we know that the mean and the variance of the Poisson distribution are both equal to lambda. One second, let me get that page back. So this means that, what does this mean? That the mean of S is equal to the variance of S equal to lambda. And so we have to divide by the mean and subtract the mean and divide by square root of variance to form this Z. So now I don't have an N here. I just have just the S. So it's S minus lambda by root lambda. So it turns out that because S, why is the CLT even applicable to the Poisson case at all? It is applicable because S can be for large lambda. It turns out that you can view this S, that is S can be viewed as the sum of IID xi, Poisson xi. Remember the important result that if you add Poisson random variables, you keep getting Poisson random variable and independent Poisson random variables. You add them, you get Poisson random variable, and so if you add n of these xi's, so let's so xi can be Poisson, let's say lambda I, e.g. I can take this lambda divide by n, right? I can divide the Poisson and the big Poisson with fat lambda. I can divide it into, chop it up into 1 by n, and so each xi let's say has Poisson parameter lambda by n, so that the sum S has a parameter lambda, and so this way of generating S says that the CLT is applicable to S and Z. most certainly it applies to to Z. What is the Z again? Z is S minus, to repeat, Z is S minus lambda by root lambda, and the probability that A is less than Z less than B, some interval probability, will be roughly equal to the probability of, let's say, A less than some, call it W if you want, but W is some random variable which is the Gaussian random variable with zero mean and unit variance. So this is very useful, because once again this is this Gaussian probability out here, right? This is a Gaussian probability which is available, right, in a computer. In any software package will be can be used to find this Gaussian probability, and this is, right, going to be equal to, or it's a good estimate of the interval probability on Z. Okay, so with this I will stop this lecture, and I think the course also maybe may end at this point. So we will maybe just take up some maybe some more examples. I'm not sure if we have, but basically the theory portion will stop with this, and so I will stop recording here.